When we're dealing with current electricity, we have taken a look at what we actually need in a circuit to have that current electricity run. But when we actually get current electricity going, we end up having a few measurable values that we can end up using to help us understand what's actually happening inside the circuit. There's basically three things that we can really take a look at. And the first thing that we should understand is what is called the voltage. The voltage is really defined as the energy per unit of charge. Now, if you actually think about what that means, the charge really comes from the electrons. Energy is really how much force is given to each of those electrons. Here's the way I like to think of voltage. Imagine sitting in a wheelie chair. So here's my little wheelie chair. I'm just gonna, there we go, that's my wheelie chair. And this person is kind of like the electron. What we need is something to actually give a push to this electron in order to get it to start to flow in our circuit. So if we have another person who comes up and they actually give a push to this person, that is very much like the voltage. The voltage is what actually forces the electrons to travel through the circuit. But once we push those electrons, they're actually going to start moving. And that leads us to another idea, which is called the current. The current is essentially how fast, or you could also think of it as how many electrons are moving. The more electrons you can get moving, or the faster you can get them to go, the greater the current is going to be. So as you push your electrons forward using voltage, you generate current. You can actually now start to see the relationship between these two things. If I were to have a high voltage, what you can really think of that as is getting a really large push to the electrons. So if you were the little person sitting in the chair, if you get a really big push, you should expect to go really fast, which means when you have a high voltage, you tend to have a high current. The other thing is if you just give a little tiny push, well, that little tiny push would be kind of like having a low voltage. And when you have a low voltage, what would you expect in terms of the speed? Well, you'd expect to have a low current. When we get something that looks like this, when we increase the voltage and get an increase in current, or decrease the voltage and get a decrease in current, this is one way that we can say that voltage is proportional to current. Now, current gets the letter I. It has to do with the intensity of current. The person who actually wrote about it first and did experiments on it first, that's how they came up with this. So it's the intensity of current. Current gets the letter I, but has the symbol amperes, which we would normally abbreviate amps, and gets the letter A. Voltage gets the units volts and gets the abbreviation V. So that's one thing we know in a circuit, is that voltage is proportional to current. But based on what I've just explained, it seems like there should be nothing ever stopping electrons. Basically, you should be able to hook up a battery, no matter what the voltage, to any substance, and you should be able to get a current out of it. But we know this isn't necessarily true. And that's because there's another property in circuits that is called the resistance. Every material that allows electrons to flow through it has a resistance. Wires have resistance, but especially loads have resistance. Things that convert electrical energy into other types of energy are actually using up a majority of that energy in order to do something else. And that other thing that they're doing, and that slowing of electrons, is what we would call resistance. So resistance is the other property that we see in circuits. And resistance is the loss of energy by electrons as they flow through a material. When it comes to these materials, loads have very high resistance. Now, it all depends on what that load is, but they tend to have higher resistances. Resistance is measured in a unit called ohms. And when we measure our resistance, we use this unit ohms, but we can't use an O as a unit, because then if you had like 4 ohms, how do you know if it's 40 or 4 ohms? And so what we use instead is a Greek letter for O, which is omega. And in an equation, what you would see is this gets the letter R. So resistance is the letter R, but is measured in the units ohms and gets this as its symbol. Okay, let's go back to our analogy. We had our electron. It's like our person sitting in our little wheelie chair. We have our voltage. That's the person who is actually going to push the wheelie chair and generate the current. So we have our current that's coming out of the push. The push itself, well, that was the voltage. But when you push a person on a wheelie chair, it kind of depends on a lot of things. It can depend on the surface that they're traveling through. It can depend on the wheels. But essentially, the force that they are pushing against is the resistance. If you think about resistance and you think about current, you can see there's going to be a relationship between the two. As energy gets taken away from the electrons, they're not going to be able to travel as well. So there is actually an inverse relationship between current and voltage. The higher the resistance, the harder it is for electrons to flow. It's like having really sticky wheels on your rolly chair. You can push really, really hard, but because it's really hard for those wheels to travel, you're actually not going to go very fast. It's almost like driving a truck through mud. You may be working the engine very hard, but it's actually not going to move very well. And that is kind of what resistance is like. The other thing is you can see a relationship between the voltage and resistance as well. As the voltage increases, you can actually, as the resistance increases, you actually need more voltage to overcome the difficulty in the pushing of electrons. If the resistance gets lowered, you can actually lower the amount of push to get your electrons traveling through a material. The relationship between all of these things is really important in a circuit. You see, we can actually think about all of these relationships. We talked about how voltage is proportional to the current. The higher the push, the greater the speed. But there is another relationship as well, and that is that as the voltage goes up, as the resistance goes up, the voltage must also go up. So voltage is proportional to resistance. The other relationship that we have going on here is between the current and the resistance. And if you actually think about the relationship here, the greater, or like the harder it is to actually move, the lower that current is actually going to be. So if you were to say like push the same amount, provide a constant voltage, then a higher resistance is going to mean a lower current. And what this tells us is that current has an inverse proportion, or is inversely proportional to the resistance. So essentially, if you were to increase voltage, you would increase resistance as long as the resistance, or sorry, if you increase voltage and it would increase current as long as resistance remained constant. If you had the current remain constant and you increased the voltage, you would need an increase in resistance in order to have that speed stay the same. But if you held the voltage constant, the actual amount of push given to the electrons, if you had an increase in current, that would have to be due to a decrease in resistance. This relationship between all of these ideas is called Ohm's law. It explains what we see between voltage, current, and resistance in a circuit. And it is actually a mathematical equation. Because it is a scientific law, it is that the voltage in a circuit is equal to the current in the circuit multiplied by the resistance of the circuit. This is all due to this relationship between these three things: the energy given to electrons, how many or how fast they travel, and the amount of energy that they lose as they travel. So hopefully this helps you understand a little bit more about what Ohm's law is and how these three things are related.